Hi! So today we're going to be talking about problem solving, processes, and techniques for that. So in our book, it talks about methods of problem solving. There's a man named George Poilea. I have no idea how to pronounce it. I'm sorry. And he created a 4-step process that can help you problem solve. The process goes like this. So 1, understand the problem. Obviously, before you start solving a problem, you got to understand what you're solving for, right? So that is the first step. The second step is to develop a plan. This is where a lot of people have problems and start to struggle. The secret to developing a plan that is effective is to think about which problem solving strategy fits best. So some problem-solving techniques are find a pattern, adopt a new point of view, solve a simpler problem, work backwards, draw a picture, guess and test, account for all possibilities, use logical reasoning, and use a variable. The third step is to carry out the plan. Start using math to figure out what the answer is. And then number 4 is to look back. An essential part of problem solving is having the ability to be reflective in thought. We should ask ourselves whether your answer is feasible and correct, what worked, what didn't work, and will the solution to this problem assist me the next time I see a similar problem. With that, let's get into a couple of the problems for 1.2. Sorry, my bad. Reading this, it asks, before the election, you want to determine the number of possible president, vice president combinations for the club you belong to. If both positions are chosen from 7 people, how many combinations are possible? Let's draw out 7 people really quick. 1, 2, 3, 4, 5, 6, 7. Okay, so one way of problem solving is to recognize patterns, like I've said before. Let's just test this out first. Let's say we have the red be president. If the red is president, that means that red can no longer be cannot be vice president. So that leaves us with 6 more opportunities. 6 different combinations. So here's 1, here's 2, here's 3, here's 4, here's 5, here's 6. And that's for red. If we think about the pattern, we can bring this down. So there's 6 different combinations with red. Here is 1, 2, 3, 4, 5, 6. For purple, there's 6 combinations for purple. We can assume that this pattern is going to follow. So we can take 6 times 7 because there are 7 people, and 6 times 7 is 42. So our answer is going to be 42 combinations. With that, you can kind of see how noticing a pattern can help you, and also to draw a picture. The next problem, I'll come back to this in a minute actually, because this one will take a little bit longer to explain. This problem says, what is the 1s digit in the number 3 to the power of 2056? It's a start with smaller exponents to find a pattern. So to do that, let's say 3 to the 0th is equal to 1. 3 to the 1 is equal to 3. 3 to the 2nd is equal, 3 squared is equal to 9. I almost read 6. 3 cubed is equal to 27, and 3/4 to the 4th is equal to 81. And if we went on, we would start to notice that it goes from 1 to 3 to 9 to 7, and then back to 1. Knowing this, we can take, that means there's 4 different 1s options. 1, 2, 3, 4, which is 1, 3, 9, and 7. So if we take we can kind of assume that if it follows this pattern, well, maybe we could write out some more first just to prove what we're trying to prove. So 3 to the 5th is equal to 243. 3 to the 6th is equal to 729. My bad. 3 to the 7th is equal to 2,187. 3 to the 8th is equal to 6,561. And we can see that 1397 pattern. 1397, 1397, and we can assume that it will continue being 1397 in the ones place. Now, one thing that we can try to see if it will stay consistent, to see if we'll be able to test the 2056, is to take 3 to the 8th, or we'll take 4, and then we'll divide that by 8. That will give us 2. And then if we look at the 2, 3 to the 2nd, it will give us 9. Well, that doesn't seem to really fit very well. Give me just a moment to think. 3, let's do 7. 4. 7 divided by 4. 4 goes into 7 one time, which will give us, 4, and then 3. So 1 remainder 3. That will give us 1.75. I think that we want to look at the remainder, because if we take 3 to the 7th and look at the ones plates, it's 7. And if we look at the 3 to the 3rd, it's going to be 7. And if we think about 3 to the 8th, 4 went into 8 2 times with a remainder of 0. And when we have 3 to the 0th, it will give us 1. And we could try that with the others, but I think that our pattern sort of fits, where we divide 4 by whatever exponent the base is raised to. And then we can look at the remainder and then compare to these first 4 exponents that we tried. So 4 divided by 2056, that gives us, 4 goes into 25 times, so that'll give us 20. Bring the 5 down. That goes in one time. 4, remainder 1, 2, 6, and then 4. So 504, remainder 0. Our remainder is 0. We can assume that our ones place is going to be just this one right here. That is going to be our answer. Our ones place is going to be 1. And to plug that into our calculator, I don't really think our calculator is going to be able to handle it, but we can try. Yeah, I doubt it. It's going to be a huge number. Yeah, overflow error. It's way too big. Way too big. But we can assume that based on this pattern, it's 1. It was a little bit hard to understand, and I hope I explained it well enough. This next one is a little bit tricky as well. It's basically Sudoku. It's asking us to place the numbers 0 to 8 inclusive in the magic square so that the sum of the numbers in each row, column, and diagonal is the same number, 12. It doesn't want any repeats. So here, 0, 1, 2, 3, 4, 5, 6, 7, 8. We have used 5 and we have used 8. Thinking about this, we have 12. We can think that how many more do we need for 5 to equal 12? And that will be 7. So we know that our number can't be more than 7, which is okay because we already are not able to use 8. And then we look at 8, because I'm trying to determine this middle number right here. If we look at 8, we can think, how many more numbers does 8 need to become 12? And the answer is 4. We don't want this to be greater than 4, because if we do, it will be greater than 12. So this number can be 1, 2, 3, 0, 1, 2, 3, and 4. And then if we do have that, 0, 1, 2, 3, and 4, if it is 0, 5 doesn't really work because you're going to need 10 for that to equal. You're going to need 10. Oh, nope, sorry. I was thinking of a different problem. 0 doesn't work because you need 7 for that to equal 12. So 0 doesn't work. 1 doesn't work because you need 6 for that to equal 12. 2 doesn't work. Well, wait. 2. No, 2 would. And then, well, let me think for a minute. 2, 7. 2 wouldn't work because we've already used 5. 3 could work because that would leave us with 8. Well, oh, wait, just kidding. Oh, no, never mind. That would leave us with 8, and then we would need a 4. And 4 is still open to us. And 4 would work because that would leave us with 9 in this 5 row. And we would need 3 more for it to equal 12. So let's leave this 3 and 4 here. If we chose 4, well, if we chose 3 for 8, this would have to be 1. If we chose 4, this would have to be 0. If we chose 3, we would be able to have 6 here, and then we'd be able to have a 6 here. That was the same type of thing. If we chose 4, which would lead to us choosing 0 here, we would have to have 7 for the 5 to equal 12. So 5 plus 7 would equal 12. And then from there, if we chose this, we have 6 plus 3 equals 9. In that case, 9 plus 3 equals 12. 3 is not going to be our option because we cannot have repeats. That's what the inclusive is talking about, I think. I don't know if that is a keyword that gives it away, but I just know that it doesn't want repeats. So 3 is not an option. Let's take away all of our 3 options. 7 plus 4 is equal to 11, so this would have to be 1. 4 is our only option here, by the way. 0 and then 7. 5 and 7 equal 12. 5 and 4 equal 9 plus 3. 8 plus 3 plus 1 equals 12. 7 plus 3 plus 2. And then 5 plus 1. Hold on. Yeah, 6. And 12 is equal to that in all directions. And we can double check our answers. 0, 7, 2, 4, 6, 1, 8, 3. There you go. These are a little bit tricky because a lot of it feels just like guessing. But if you use thoughts like that, where you have the different options and the corresponding choices for that option, you can slowly eliminate it. It's easier than just blindly guessing numbers. This next question says the product of 2 whole numbers is 546. So the product means like times, multiplying. So x times y is equal to 546, and x plus y is equal to 47. There's not really an easy way to do this. I feel like it's guess and checking. We can make educated guesses. We know that it probably is not going to be 1 because 1 times 46 is just 46. We would know that. We know it's probably going to be in the 20. Both numbers are probably going to be around 20. Just because we want it to equal both these and these respectively. So if we try 20, well, let's make a little table. Okay, so number 1, number 2. Well, actually, let's do sets of numbers. Product. Quotient. Oh, wait, not quotient. let's do sum first, just so I can do it in order. So, let's just start with 20 first. We're going to need 27 for it to equal 47. All of these sums are going to equal 47. What is 20 times 27? That is 540. We need 546, so that doesn't quite work. Let's try 21 and 26. That will equal 47. That will give us 900. Oh, wait. Nope, I did 46 instead of 20. My bad. That will give us 546. We kind of got lucky there with how quick we stumbled onto it. I was expecting that we'd need to fill out quite a few more, but we already have it. So the answer here would be 21 and 26. Okay, this next problem says Neil needs to mail a gift card to his friend. He uses 44-cent stamps and 7-cent stamps to pay $2.25 in postage. How many of each stamp did Neil use? So this one also deals with two equations, but we can actually just think this one through. So here's the 44-cent stamps. Actually, let's make a table of 4. 44. Number of 44-cent stamps. Like the total, and then the cost, and the number of 0.07. I don't know why that's so hard for me to write. And then cost. One thing that we can do in the very beginning is how many 44-cent stamps can he buy that is below $2.25. And we know that this is what we want to compute, because we know it's not going to be more than $2.25, and it's easier to work with the bigger numbers first. So 5 times 44 is going to equal, well, the 5 times 0.44 is going to equal $2.20. If we add 44 to this again, it'll exceed the cost. So we know that the highest number of 44 stamps that we might buy is going to be 5. It's not going to go any more than that. So let's count down. 5, 4, 3, 2, 1, and 0. For 5, we already calculated that. It's $2.20. Let's do 4 times 44 cents. That will give us 1.76. 3 times 44 is going to give you 132. 2 times 44 is going to give you 88 cents. And 1 is going to give you 44 cents. So it's easiest to start with the biggest one. We know that there's 5 cents left in $2.20 if we want to reach $2.25. And that doesn't really work with the 7, because then we would be over $2.25. So we don't care about this 5. The 4, let's do 2.25 minus 1.76 to see how much we're going to need left, like how much is left over that we need to pay. And this is going to give you 49 cents. We know that 7 goes into 49 7 times. So we're probably going to use 7 stamps. 7 cent stamps to give us the extra 49 that's needed. So our answer is going to be 4 44-cent stamps and 7 7-cent stamps. Hopefully that made sense. If you have any questions, please let me know. Now I'll move on to this question. This one. Find the sum of the whole numbers from 1 to 840. So this one is a little bit more tricky, but it also follows a pattern. So one way to see if we can spot a pattern is to start small. So if we have something like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Let's see if we can notice some things. So 1 and 7 equals 8. 2 and 6 equals 8. 3 and 5 equals 8. And then we have an extra left over. Actually, I'm going to do it with, hold on. I'm going to do it with an even set just to make it easier. It works with odds as well. It just is easier to demonstrate with evens. So 1 and 6 equal 7. 2 and 5 equals 7. And 3 and 4 equals 7. The first guy who... It's a joke that... like the person who came up with it was probably some old like Greek student who, as a punishment, was told by their teacher to go out and count find the sum of all the numbers from 1 to 1,000 before you come back in here. And then he came back in like a lot more earlier than she expected. Yeah, it's a math joke, so don't expect too much. Anyways, they say that he found a pattern, or rather, we can say there's a pattern that each of these, with our pairings, they add up to one more than the final product. And we know that for the amount of numbers, there's going to be half as many pairs. So we have 6 numbers, but there's 3 pairs. So, and then when we times the number of these two together, like 1 plus the final number, times it by the amount of groups that we have, that it's going to equal our our sum, which is 21 in this case. If we thought, well, this example would work for any set of numbers, but if we thought about it, equation-wise, we could say sum is equal to the amount of numbers you have. So in this case, it would be 6 divided by 2, because we want to see how many pairings there are. So there's 6 numbers, divide by 2 to see how many pairings. There's 3 pairings. This will give us 3 for this outside. And then we can have that times 1 plus the final number. Because this is going to give us, in our case, 7, right? And we want 3 times 7 because there's 3 pairs, like 3 sevens from this. Hopefully that makes a little bit more sense. The professor can explain to you a little bit better if you have any questions, or I can explain to you better in person if you'd like. Anyway, taking that knowledge, we can say the sum of 1 to 840 is going to be 840 divided by 2, because we want to find how many pairs there are, times 1 plus 840, because if we look at the pattern, it will be like correct, like that. Like it will work out with the pattern. So 840 divided by 2 is equal to 420. That means there's 420 pairs. And then 1 plus 840 is 841. And when we times those together, we're going to get, let me make sure I did that right. We're going to get 353,220 as our sum. It's really large, but if you think about it, it makes sense why it's so large. Hopefully that made sense. It's kind of a lot to think about. Kind of a harder concept for me to grasp. When I learned this last semester, and when I was redoing the review for this, I had to finally look it up because I didn't remember what it was when it was explained to me. So that doesn't mean like that there's anything wrong per se. It's just that it's a tricky one, and it's okay to need help and ask for questions. But I did try really hard to think about it because I knew that there was a pattern that they had found out. I just couldn't figure it out quick enough. Anyway, we covered kind of a lot in this video. Hopefully everything made sense. If you have any more questions, please just let me know. I know that this unit is a little bit harder to grasp. Thanks.